Good afternoon. I am Praveen Kumar, Deputy Director, Planetary Science and Exploration, Science Program Office, ISRO Headquarters. Welcome all of you to the second day's lectures. Today's first lecture is on Introduction to the Solar System by Professor Debabrata Banerjee, Physical Research Laboratory, Ahmedabad. And the moderator of today's first lecture is Mr. Sri Rak Nambiar, scientist at Physical Research Laboratory. He is working in the area of modeling and space instrumentation in the field of interplanetary dust science and planetary lightning. Over to Mr. Sri Rak. Sri Rak, please unmute. Not able to hear.
Sri Rak? I have good afternoon to everyone. I am Debabrata Banerjee. I'm a professor and the deputy head of the Planetary Science Division. And my primary interests are planetary science, understanding the evolution, origin and evolution of moon, and also luminescence dating, understanding terrestrial processes on Earth and time scales of landscape evolution on surfaces, various surfaces on the Earth, including fluvial sediments, aeolian sediments, and wind terrestrial wind-blown sediments as well. I have recently proposed a couple of instruments for the one for the Mars lander, the proposed Mars lander mission, which is basically an luminescence dating instrument, which will hopefully determine the first stage of wind-blown sediments on Mars. And the other instrument is proposed for the ISRO JAXA LUPEX mission, the lander mission, where one wishes to understand the volatile transport on Moon. And this can be done by determining the activity of 46.5 keV line, the gamma line, which is produced by lead-210, which is a radioactive isotope in the uranium-238 decay series. And also, we would like to understand and detect whether there is creep in the polar regions for the first time. Besides this, I have coordinated the Planex program between 2014 and 2020. And this supported many projects, almost more than 50 projects in ISRO's planetary exploration program, and several universities and IITs were supported under themes which were basically related to remote sensing, modeling, atmospheric modeling, modeling of planetary atmospheres, remote sensing instrumentation, and meteorite research. At the moment, at present, I have published 56 papers in national and international journals. Thank you. So Dr. Praveen. Presentation will focus on introducing various objects in the solar system, and then also I will give a flavor of as to how the solar system evolved to its present state, and how how did some objects, major objects in the amongst the inner planets and the satellites formed and evolved to its present state. And then and I will also tell about how one can date solar system objects. That is, determine the time scale of early solar system formed objects. So you can see this. You know, as you see the solar system, you start with the sun. This was described in some detail by Dr. Das yesterday, and then we have the inner planets, which are composed of Mercury, Venus, Earth, and Mars. And then comes the asteroid belt, and then you have the outer planets, which include the gas giants, Jupiter and Saturn, and then the ice giants, Uranus and Neptune. Now, Pluto is seen there, but Pluto now, as you know by now, is not considered a major planet. It's now a dwarf planet, as per the International Astronomical Union's definition. So solar system objects range in size from a few microns to which is basically regarded as dust, to giant planets. And information exists at all scales which tell us about the origin and evolution of the planets, which has been a basic research, a fundamental research area in the last 3 decades or so. In 2006, the IAU, the International Astronomical Union, has defined the planet as, it is given a proper definition, that the planet must orbit the sun. Each planet must orbit the sun, and then it should be sufficiently massive, and it should have a spherical shape, and it should have cleared the region around its orbit of large debris. So now, because of the third property of this planet, of planets as classified by IAU, we now consider Pluto as a dwarf planet, and not as a planet, which was the case, 4 decades ago, or even 3 decades ago. So dwarf planets are the first 2 properties, but not the third criteria. So Pluto became a dwarf planet as is series. Now, then you have the asteroid belt, which is there between about 2.2 AU. One AU is basically 150 million kilometers. This is the distance. This is shown here. This is the distance between the Earth and the Sun, and most of the distances are classified. Most of the planets, when we talk about the orbit, we discuss in terms of AU, as you see here. So asteroid belt is basically between 2.2 and 3.2 AU, And these objects are very significant in the sense that they represent residue from the planet formation process, and they have undergone thermal or chemical processing. So I will come back to this table. Let's go to the formation of planets first. So at 4.5 billion years ago, to be very precise, it's 4.567, and we know this. This was a question asked yesterday, I believe. We know this because we can perform radiometric dating of early objects, early solar system formed objects. And there are also short-lived radionuclides, which can be used to date calcium, aluminium, CAIs, basically, inclusions. And then there are other objects which can be also used to date, like chondrules, which is one of the earliest found objects. So 4.56 billion years ago, the solar system, there was a giant molecular cloud, okay, which contained interstellar gas and dust. The cloud collapsed, and then possibly due to a shock wave of a nearby exploding star, which may have been a supernova. And then solar nebula forms, spinning, swirling disk of material. From this disk, then the sun forms, and then matter further out in the disk clumps form larger and larger objects. So some of them, basically, they will accrete. So you have planetesimals, which are very small objects, which have accreted to form planets. And then you have other objects which are called dwarf planets and large moons, which exist in the solar system. In some cases, the planets could not form, particularly in the asteroid belt, and there you have, if you study asteroids, if you can go and have a sample return mission from an asteroid, then one can actually study one of the first solar system formed objects, and how it formed and how it originated and how it evolved to its present state. Other objects in the solar system are comets, meteorites, and moons. So if one looks at various characteristics of the solar system, so you can see there, okay, I have given certain colors. So you have the inner planets, which are labeled in rocky planets. These are basically rocky planets when you can see the densities there, okay? So if you see Mars as a density, this is the bulk density note. This is different from the crustal density, which, for example, in the case of Moon is around 1.6, but the bulk density is larger because you have the crust, mantle, and the core, right? So you have densities of the order of 4 to about 5, the bulk densities, and Moon is at 3.35. Then you have other objects, the gas giants and the ice giants, and note the densities, the difference in densities between the gas giants and ice giants. So now you also have the dwarf planets, okay, which are noted which are colored in orange or brownish. Given, and these include Ceres, Psyche, Vesta, and Pluto. The mean radius of Ceres is 470 kilometers, and if you notice the gravities, basically Earth has, as you all know, Earth has a gravity at 9.8 meters per second square, and it has an atmosphere and a magnetic field, okay, associated with it. However, if you have a small object, then it is very difficult to hold the atmosphere, and therefore some of these objects are atmosphereless, as you will see in the forthcoming slides. The temperatures are given there, and this will be discussed in more detail later. Most of the planets have prograde motion, but there are the Venus, for example, is one which has a retrograde motion. So therefore, it is pretty slow. This means that basically, the central star, right? So you have the central star, basically, which is the sun, is moving and all the other objects are moving in one direction, but the Venus moves in the opposite direction, clockwise, and the others are moving in the anti-clockwise direction. So therefore it is slower, and there are reasons, and this is a big, there are debates as to how Venus, what gave rise to its retrograde motion, whether it is tidal locking between the sun and or basically tidal locking between Venus and sun, because Venus is very close to the sun, and the atmosphere heating, Venus is very hot and the atmosphere gets very hot. So therefore, these two forces are basically acting against each other, and therefore you have a motion which is opposite to that of the central star. Now, in this slide, I have outlined the mean radius, mass, bulk density, and orbit. And actually, this was a longer presentation last year, but I have to note the time as well this time. So if you notice the surface temperatures, Venus, if you notice the sizes of Venus and Earth here, they are almost the same. The mean radius of Venus is 6,000 kilometers roughly, and of that of the Earth is about 6,400 kilometers. So one may argue what led to this runaway greenhouse effect, which has affected Venus which has basically given rise to this surface temperature of 740 degrees. Why did Venus evolve to this state? And this is one of the major outstanding questions which is yet to be resolved properly. So Venus surface temperature is 740, Earth is milder, and Mars is cooler because it is further away, 223 Kelvin. Mercury is the temperature varies between 100 to 700 Kelvin. At night time, you have very low temperatures, just as that on Earth, and not on Earth, on Earth's moon, and particularly in the permanently shadowed regions of the moon, where temperatures can be as low as tens of kelvins, about 40 Kelvin or 50 Kelvin or so. The magnetic fields, and you notice that Earth has a magnetic field it depends on where you are, so it's between 20 and 60 microtesla. The others, you see, the larger planets also have large magnetic fields, but Mercury doesn't have a magnetic field, and neither does Mars. Not a significant one. It's about 20 nanotesla, and on Mercury it's 300 nanotesla. And one of the questions is whether Moon had a significant magnetic field in the first 10 million years or so. So if we can do paleomagnetism of some rocks which are returned from the Moon, perhaps we can address this question. So if one looks at the atmosphere, the major constituents, you can see that Venus has a very thick atmosphere of 93 bar. But if you go about 50 kilometers above the surface of Venus, then the surface pressure is the pressure there is comparable to the surface pressure of that of the Earth. Okay, if you go to the Venetian clouds, Mercury has no atmosphere, the Moon has no atmosphere, and Mars has a 6.5 millibar atmosphere. This is at the surface, and the main constituents of Venus and Mars are carbon dioxide. Earth is the only habitable planet. So this is also one question: how did life originate? Say about between 3.5 to 4 billion years ago. Why we have not detected any life on the other objects which we have explored thus far. And then you have Jupiter and Saturn, and maybe in one of these moons, okay, of Saturn, one may find a primitive form of life existing below the oceans. Okay, so I will move on more quickly. So asteroids and comets have origins from the solar nebula and provide samples suitable for dating formation of the solar system. Meteorites mostly originate from asteroid belt, but many are from the moon and some from Mars, and some meteorites are derived from asteroids which have experienced differentiation. So you will hear about this in the next lecture from Professor Kuljeet. And I'm just giving you some introduction. Chondrites contain spherical chondrules. So ferromagnesian, minerals, basically olivine and pyroxene, between 0.1 to 2 millimeters, and studies suggest that they solidify from a melt. And then you have a group of meteorites, HED, which is basically Howardites, Eucrites, and Diogenites, which originated from a single parent body, the West asteroid, based on chemical classification. And then there are irons as well, which have come from the cores of asteroids, which have broken up as a result of planetary melting. So planetary bodies, as I've said, they form by accretion of grains that condensed from the solar nebula, and then centimeter-sized objects grew to meter-sized objects, and then kilometer-sized planetesimals, and then finally there were more and more collisions, and accretion led to the formation of larger sized bodies of the order of 3,000 kilometers. So some fundamental questions I wish to put forth here as to why life originated on a, how did Venus acquire its dense atmosphere? Why Mars is a very thin atmosphere and Moon has no atmosphere? So maybe some of you can look into this. Let me go into now. I will discuss something about the origin of the solar system. So the first solids, if you look at even without dating, radiometric dating, if you look at the first solids to condense, these are refractory. Okay, so they have high melting points and low vapor pressure. So in nature, so the first solids to condense are shown there. Okay, corundum, perovskite. Okay, spinel. Then these are different minerals. Okay, and if one can date, if there is a way of dating the first form solids, okay, then one can tell the age of the solar system, which was a major question. Okay, so now if you look at this, now I'm showing you different solids. Okay, so you have on the left, you can see refractory oxides, and then you can see pristine material, and then you can see that there are two things. One is differentiation, the other one is one body is differentiated, the other is undifferentiated. So differentiation is a process where basically you have melting of the entire or part of the object, solar system object, due to radioactivity and due to heat of accretion, if it's a large object. And then you basically can differentiate different kinds of objects. So because I have been limited to 35 minutes or so, I will skip some slides, but you can have undifferentiated objects. So this includes meteorite falls, which are chondrites and achondrites. And you can have differentiated objects, which include stony irons, irons. So amongst these, okay, differentiated objects, you have Martian meteorites and lunar meteorites as well. And then the carbonaceous chondrites are extremely primitive, okay, ordinary and carbonaceous chondrites, and these are undifferentiated objects. So how do we actually analyze these samples? So you have, the samples are meteorites, okay, primitive meteorites, and sample returned from missions. And we will also have missions to the moon, Mars in future, and other objects, solar system objects. And then one can analyze the stable isotopes, the radioactive isotopes, using the instruments which are mentioned here, and sample characterization can be done, which includes elemental and mineralogical composition. So just to highlight how this is done, okay? So basically, you see, there is, there are isotopes. Okay, so aluminum 26 is the one. And, there's a lot of research which went on in the early 90s and the next decade in PRL itself. Basically, aluminum 26 decays to magnesium 26 with a half-life of 0.72 million years. And based on this, you see, so if you have the, in this slide, you can see somebody asked regarding this. Okay, so this is the short, this is how you can date these early solar system formed objects. So the first solids to condense were the refractory objects. Okay, and the time scale is linked to the origin of the solar system. So basically, if you look at, if you want to detect these are relative time scales, okay? So what one needs to do is measure basically the aluminum 26 by 27 ratio in CAI. Here I've shown chondrule, of course. This is how you determine the time scale of age of chondrules. But basically, by looking at aluminum magnesium systematics, one can determine the age of these early solar system objects. So this will be discussed in more detail. However, let me give you a flavor before ending in the next 7 to 8 minutes. Let me give you a flavor as to how, what are the instruments which are flown and what are the objectives related to these instruments, okay? So basically what we do is we look at particles, okay? That means they have mass. So we look at protons, alpha particles. We need to detect these, or we look at radiations, okay? And then waves. So these are the basic carriers of information which help us understand and detect subsurface features. For example, this is done using microwave, so radar, okay? Synthetic aperture radar. Then you have the infrared part of the electromagnetic spectrum. So this is all related to the electromagnetic spectrum. Particles are, the particle domain is a little bit different. So one should differentiate between that and the electromagnetic waves, which are basically, these are composed of photons, which are massless. So you can tell about surface mineralogy by looking at IR, which is reflected back from the surface of moon, okay? And you can tell whether there is water present, as was done for the first time, in fact, water was detected by the moon mineralogy mapper on Chandrayaan-1. So this was the biggest discovery of Chandrayaan-1. And earlier there were some supporting experiments from neutron spectroscopy, but they could not conclusively tell because neutrons look at hydrogen. Epithermal neutrons tell us about hydrogen on the lunar surface. However, water is detection is only possible using IR or synthetic aperture radar, water or water ice, in fact, to be very precise. Then, if you go to X-rays and gamma rays, one can tell about near surface and subsurface chemistry. So, how did the moon? One can ask about how did the moon form? Okay, so basically, you have a Mars-sized impactor which hits the Earth and it blows out debris into the orbit. This is about 4.5 billion years ago, and it accretes, and then it accretes to form the moon. And this this theory came about. There were many other theories. One suggested co-accretion. Then there was another theory which suggested that basically the moon was the moon was already formed. There were different theories anyway. I will not go into it now. But the lunar, the giant impact hypothesis satisfies the angular momentum of the Earth-Moon system. And it also basically came about because the oxygen isotope ratio was measured for return samples, and basically the Earth and Moon falls on the same line. So that provided conclusive proof as to this theory. And then why are the volatiles lost? This also can be addressed using this theory. Why is there the volatiles such as potassium? It is in much lower concentrations as that of the Earth. So then how does it evolve? Moon forms around 4.56 billion years ago. Then accretion melting results in the magma ocean. And most of the moon melted. And then crystallization of the magma ocean. So this is basically differentiation. And then you have cooling. And then you have basically a differentiated lunar interior. So you have the crust, mantle, and core. And the heavier minerals have sunk below, and then you have an anorthostic crust. But there are also features which have to be explained. And then you have impact cratering and volcanism. So there are several lectures which will address these. So I will not go into detail. This is the radiation which we expect. So you can see epithermal neutron, which is basically the energies of the order of 1 electron volt. So this can be used to tell the composition of the lunar surface and composition of surfaces of an atmospheric body. And this shows you the number of missions, okay, which orbiters, landers, rovers, and CubeSats which are planned as well. So you see there is a, in earlier, you had the Apollo and the Luna missions, which brought back rocks. And from that, we understood how the moon formed. But then our ideas regarding the presence of water, ice on the moon changed when the M-Cube instrument detected water ice for the first time on our Indian mission, the ISRO mission Chandrayaan-1. And this has been followed by Chandrayaan-2 and Chandrayaan-3. And there are many discoveries which await us in future missions, which will take place, including that from ISRO. So some questions for you regarding lunar explorations. Did the early flux of impacts? So we really don't know much about the time period between of evolution between 4 gigayears and about 2 gigayears. Okay, and we do not know whether the flux of impacts peaked at 4 billion years or not on the moon. So these are some of the major questions. And then we also wish to assess the mineral resources of the moon and volatile transport on moon. And 2 major objectives of sample return mission from a South Pole Aitken basin. It's a huge basin in the southern part of the moon. Is basically, if you date the South Pole Aitken basin, it places limits on the early impact history and timing and duration of basin formation events. And then this is the deepest basin in the solar system. So you may have 12 kilometers or so, and you may expose the lower crust and the upper mantle. So you will get to know, you will get a better understanding of the upper mantle if you study rocks brought back from the South Pole Aitken basin. As regards Mars, I will not tell much, but what we do not know, and this is the second last slide, so I will conclude soon, is how, when, and why the environments vary through Martian history, and did any of them host life or its precursors? See, Mars, initially, it was hot and humid. It had a much thicker atmosphere than the 6 millibar atmosphere, which is prevalent today. And basically, solar wind erodes the atmosphere, because the Earth has a magnetic field, but other objects such as Mars or the Moon, they don't have strong magnetic fields. So they are not protected from particles, okay? Such as solar wind protons, which come into the atmosphere and then erode the atmosphere significantly through time. So how has the Martian climate evolved through time? What are the inventory of carbon compounds? Is there life on Mars? Did life exist on Mars? That also, but now that is moving towards, then there were questions regarding follow the water, and then which parts of Mars are habitable. So these are some of the questions then what is the internal structure and dynamics, and what are the nature ages and origin of diverse geological units. And here you can see there are less Mars missions, and we have our Mars orbiter mission as well, MOM, which was flown in 2013. This is likely to be followed by a lander rover mission in the near future. And we will have many more discoveries, and I hope some of you will be motivated to contribute to the planetary science and the solar science exploration, solar system exploration program of ISRO. Thank you, and I will conclude here and take questions.
Hello.
Life compared to Earth. So is this presuming, so the person is presuming that we will have life on Mars, so we have to adjust to the gravity basically on Mars if we think about having life on Mars. But the major problem besides the gravity is that Mars's atmosphere is very thin, so you have particulate radiation, okay, solar wind which is coming in basically. Radiation is not good. Basically, radiation has health effects, and it gives radiation dose in terms of CVITs, okay, or grays, and if it is significant, then it can have cancerous effects. So one has to worry about radiation. That is much more of a worry. If we can adjust to the gravity, you have had people on the moon, right? So 1/6, and here it is 1/3. So if you have had people on the moon for a while, presumably in future you can have a lunar outpost, okay? And one needs to think about that first rather than Mars. Then we can, think about Mars. But we have to think about radiation, and if you want to sustain, if you want people to live there, then they have to produce food. All these things are there, okay? Okay. Yeah. If light, yeah, that's only one question I see.
Yeah, there is another question from Mr. Sayan Talukdar. He's asking, does the magnetic field of any planet have any effect on its temperature?
Magnetic field have any effect on its temperature? No. Magnetic field is basically, magnetic field is deflecting any charged particle, okay? So it deflects if the magnetic field is strong, like that on Earth. I see there are many questions now. In fact, I didn't press see more before. So magnetic field, so Earth's magnetic field is half Gauss, right? So it is stopping at the equator. It is stopping galactic cosmic rays unless they are of the order of GeV, giga electron volts, okay, 10 to the power 9. So that is the kind of energy it has, the magnetic field. So to my knowledge, it does not have any significant effect on the Earth's temperature, on the object's temperature, but it will stop charged particles, and therefore, if you have a strong magnetic field as that of the Earth or on Jupiter, then you can retain the atmosphere. Otherwise, the atmosphere will erode slowly, as this has happened on Mars. Okay, so Moon is older than the solar system? No, Moon has formed after the formation of the Sun. Actually, this question should have been: is Moon older than the Sun? No, the Sun has formed first. So the giant molecular cloud collapsed, okay, under its own gravity, and then you basically have the proto-sun and the protoplanetary disk. Okay, so then you have accretion of small objects, as I said, and this becomes larger and larger objects. Okay, so some of them have gone on to form planets, and some have become satellites, but the Moon's formation is definitely younger, okay, than that of the Earth and that of the Sun. Okay, please tell more about magma ocean. So magma ocean, okay, magma ocean is basically is an important concept on Moon. Basically, the heat of accretion is 412. Yeah, so I can go on for 3 or 4 more minutes. You have the heat of accretion of Moon, right? So when it forms, you have gravitational potential energy, right? So a lot of energy is there. So basically, this heats up the early Moon, and then there is complete melting or partial melting of the Moon. We do not know this very precisely. It may have molten entirely, and if it melts, then then it will cool down eventually. Okay, that heat will dissipate and it will cool down, and then once it cools, then it will form the crust, mantle, and core. So the crust, you have on some parts initially you have anorthosites. Subsequently, because you have volcanism, okay, on the Moon, you have had basalts. So you get basalts on the Moon as well, okay? And then there are, of course, breccia, which is just a mixture of everything, okay? Okay, Mars says this one is done. How do spacecraft navigate and communicate when there are millions of electromagnetic radiation? Okay, I am not an expert on this. I am basically a planetary scientist, but electromagnetic radiation, right? So you have that's basically you have a big dish. So that dish communicates with the orbiter, right? The dish is on Earth. So you need, this is basically radio waves. Okay. I can't. Okay. Dr. Praveen, should I take a few more, or now I'll stop?
You might take 2 more questions, maybe some 3-4 minutes.
Okay, let's see now. So how do the atmospheres and planets' atmospheres and surfaces vary, and what factors influence these conditions? Okay, so how do these surfaces, planets' atmospheres? Okay, so firstly, how did the atmospheres form? Okay, so this itself is an interesting question. So it's basically, is it when the planet evolves? Of course, this depends. Okay, where you are. So Jupiter, it's basically hydrogen. If you saw the composition, right, it's mostly hydrogen. So there is something which is called the snow line or the ice line. Okay, so if you are beyond this, okay, then this depends. It depends on the material. For water, it is. Some people argue it depends on the temperature also. So 2.7, or it's in the asteroid, roughly somewhere around the middle of the asteroid belt, 2.7 AU or so. Okay, so beyond this, you can condense, okay, and you can form particles. Okay, so here the evolution of the gas giants is very different from the rock giants. Okay, so they are very close, and therefore they are condensed, and they are inside these lines. So the evolution is a little bit different, and they form rocky planets. But here you have, it depends on what is your composition, initial composition. If you are in the case of Neptune, for example, these are ice giants. You have formation of ices there. Okay, so this is one thing. This is basically depicting the atmosphere, the initial atmosphere. Now, then you have after this, okay, it depends on your gravity. Can you retain the atmosphere and the magnetic field as well? If you have a strong magnetic field, then you will have a planetary atmosphere existing today, a thick atmosphere. Surfaces. Okay, surfaces, I've told you. You can have icy surface, or you can have a gaseous surface, or you can have a rocky surface. So this basically differentiates. And then you have the asteroids and the comets also. I didn't talk about comets at all, but there are a couple of lectures. So this basically constitutes the entire solar system, our solar system. Okay, exoplanets are there, and people talk about whether there is life on exoplanets, but that will be considered later. But here, you have the inner solar system, the sun, then you have the inner solar system, rocky planets, then you have outer gas giants, asteroid belt, then the gas giants, and the ice giants. Okay, and then Pluto, which was earlier considered, and there's been a mission as well, from NASA to Pluto as well, but it is now considered a dwarf planet. Okay, thank you so much. So I will close here, and you can, I think my email can be shared if you wish. I can address some more questions on email. I think Dr. Praveen can.
Yeah.
Yeah.
Thank you, Professor Deba, for a nice lecture, and also to Mr. Srirag for comparing this session. Thank you so much for both of you. And of course, we will collect few questions and share to Professor Deba to answer those questions to the. Maybe we will see how to put these answers in the portal. Thank you so much. Now we will hear the third lecture of the series, and today is a second lecture on the formation of the solar system by Professor Kuljeet Marhas, PRL, Ahmedabad. Moderator of this lecture is Mr. Vikram Goyal from PRL. He has been working in the field of planetary science for the last 7 years. He manages the sophisticated mass spectrometer that is a very popularly known as NanoSIMS at Physical Research Laboratory, Ahmedabad. Over to Mr. Vikram.
Thank you, sir. So today we have Professor Kuljeet Marhas here. Kuljeet Marhas is a professor and head of planetary laboratory section at PhD at Physical Research Laboratory, Ahmedabad. She pursued her PhD in physics from same institute, followed by postdoctoral work at Max Planck Institute from Mainz, Germany. She was a research associate at the Laboratory of Space Sciences, Washington University, St. Louis, USA, before joining PR. She also worked as a Fulbright Fellow at Astromaterials Research and Exploration Science, Johnson Space Center, JSC, Houston, as a visiting scientist in 2015, and at Carnegie Institute of Sciences in 2023. Her research interest lies in planetary sciences, emphasizing isotopes and elemental study of meteorites and other extraterrestrial materials, specifically sample return from the missions, along with the organic and volatile studies that further our understanding of the origin and evolution of early solar system. She is recipient of INSA Young Scientist Award, Women Excellence Award, Eminent Mass Spectrometrist Award, DILA Memorial Medal, She has also received Fulbright Nehru Academic and Professional Excellence Award, United States India Educational Foundation 2022-23, and is a SERB Power Fellow 2021. She is a conferred Fellow of American Geophysical Union 2019 and a Kavli Fellow of US National Academy of Sciences 2015. Over to you, Professor Kuljeet.
Thank you, Praveen, and thank you, Vikram. I'd like to share my slides now. formation of the solar system. So you have heard and seen this figure many a times right now, right? So what I want to say here is that we have to make a model for formation of solar system. In order to do so, you should understand what exists, what is there. And this can be only done by the observation or the laboratory methods. By observation, we know that we have one star, 8 planets, out of which 4 are terrestrial planets, inner planets, and then 4 giant planets, out of which 2 are gaseous, 2 are icy kind of planets. So we have 8 planets. Few planets have moon around it. And if you calculate the total number of moons that have been detected till date, is around 293 moons. You can also call them satellite, because we say moon for our Earth satellite is known as moon. But a general term, moon means the satellite around the planet. So there are around 293 moons of satellites that have been detected till date. There are 5 dwarf planets. You have heard what are dwarf planets from Debabrata. And the asteroids that is a belt between Mars and Jupiter, you can see here dotted lines, are around 1.3 billion asteroids. And the comets that come from the outer region of the solar system is around 3,900 known comets till date. Okay, so there are many objects in the solar system. So if you really want to study them and come to a conclusion of formation of solar system, it is pretty immense work here. So any theory to describe the formation of our solar system must be consistent with the observable facts. So other than this, we need to know all the observation facts, and then we'll come to the laboratory analysis facts. And I'll try to modify the formation of solar system with you and see which one suits better. Yeah. So the first challenge is the pattern of motion. You know this already, but let me go through it still. All planets orbit around the sun in the same direction, which is counterclockwise as seen from the Earth's north pole. Planets' orbits are nearly circular and they are co-planar. Planets rotate in the same direction which they orbit. Almost all moons orbit their planets in the direction of the planet rotation. And last, the sun rotates in the direction planets orbit. So you know that everything seems to be similar, going similarly. This is the first challenge you have to explain. The second challenge was to explain between these 2 distinct group of planets that I showed you just in first slide. So that they have the first 4 planets are known as terrestrial planets because they have a solid surface, and these are very close to the moon. They have small masses or radii. They are very rocky, solid surface. The density therefore is very high. Their rotation is very slow. They have a weak magnetic field, as Debabrata was showing, and they don't have rings like outer planets, and they have very few moons. Now compare this to the Jovian planets. Jovian planets are the outer planets like Jupiter, Saturn, Uranus, and Neptune. These are far from sun, large mass, large radius. They have gaseous surface. They are low in density. Their rotation is very fast, and they have strong magnetic field compared to the terrestrial planets. They have many rings, especially Saturn, if you know, and they have lots of moons. Yeah, hundreds of moons in Saturn itself. Yeah. So the question for the second challenge is, why is the inner part so different from the outer part? There is a distinct difference between the two. I mean, the observer that you can observe very easily. Yeah? The third challenge is to explain the asteroid belt and the comets that come from far off. Yeah. So the asteroids are small rocky bodies that orbit the sun, mostly between Mars and Jupiter, as I show. It's called an asteroid belt. There's a classification to asteroid belt too, which I'm not discussing today. But as I said, there are 1.3 million asteroids that have been discovered. As of comets, they are small and icy body that have spent most of its time beyond the orbit of Pluto. So as I said, 3900 comets have been discovered. And actually, comets occupy 2 regions. One is Kuiper belt region and one is Oort cloud. I didn't talk about Oort cloud this time. There may be something else, but you have to know that there are two regions of comets from where the icy body comes. So from this, we know there is an existence and there is a property of these small bodies too. They are large in number, but they have their distinct properties. Yeah, this is asteroid is more like terrestrial thing, and comet is more like outer material, right? So now the fourth challenge, that is exception to the rules, yeah, which don't follow the rules I talked about, yeah. So like Mercury has a large eccentricity, orbital eccentricity, or Uranus is very tilted, yeah, in rotational axis, or Venus rotates backward. It is clockwise. Everything rotates counterclockwise. This is clockwise, yeah. And Earth has a large moon comparatively to other moons that you see. So that these are some of them. There might be many exceptions which you would like to put in, but as of now, let's go with this, yeah. So the least that a theory should deliver is convincing explanation to the gross features first. These small features probably you can still explain later on. First, the gross things we should be able to explain for any model of formation. So since 17th century, people have given various models. I think there are around 10 to 12 different model of formation of solar system. So if you go to Google and check various model hypothesis of solar system formation, you'll find immense number of them, yeah. But let me just put forward 2 or 3 just for the sake of the feeling that there were many things that were going on from 17th century to say till now 21st century. We are still fiddling with the formation of solar system, right? Still we have not come to a conclusion of a real good model for solar system formation, yeah. So let's see if you find this very interesting. So first one is Laplace nebular theory. This was given earlier in 1750 and it has continued. It has been this is the one theory, nebular theory, which has been taken till date, yeah. But so it started with it says that there is a cloud kind of a system, and this becomes oblate because of the rotation and flattens, and then there is a star and the planets form together, yeah. So the problem with this kind of system was that the differential rotation between the inner and outer parts of the rings would prevent the material from condensing. The planets wouldn't form the kind of system they had given. This is not a detailed version. I would expect you to read a detailed version if you really want to know about this. So another one was tidal theory, that the sun was already there and a star passing by. Due to the pull of the star, the material from the sun made a filament kind of a structure, and this filament is forms the protoplanets and planets eventually. So this has its own kind of every model that was given has its own kind of problems associated with them. The most important problem associated with this was, so if you do a theoretical modeling to this, I mean, there are many. First is that sun and planets give the same age, whereas here it is not. And second is that you cannot make anything beyond 4 solar radii, which is like within Mars orbit, you need to form all the planets, yeah, if this is the condition, tidal theory. So these didn't work out. Another theory which I found very interesting was that there's a sun and then there's a star going by, and the protostar's material is captured by the sun. Instead of star capturing sun's material, this is other way around, and it makes a circle around the sun. Again, you cannot explain. You will need millions of such protostars to move around sun to capture the amount of material that we see as of today around sun. So again, this was not, and there are many more. Yeah, you can check this out. Now, the other parameter that I would like to include when I'm talking about formation of solar system is that you analyze some samples in lab and see the isotopic and elemental workings, or do a chronological measurement of these to understand when it was forming, so that you can give a very concise and a better solar system model. So many samples have been measured. I hope you know meteoroids come mainly from the asteroid belt. So 2 asteroids hit each other. due to a resonance created by Jupiter in general. And these, when they hit, a material from asteroid comes out. And when they enter the interstellar medium, they are called meteoroids. When they come into the Earth's atmosphere, it's called meteors. And when it falls on the Earth, it's called meteorites. So these meteorites, we collect these meteorites and measure in lab. We have meteorites, around 4,000 meteorites that have been collected worldwide. And there are also some from Moon as well as Mars. So we have free samples from Moon and Mars. We didn't have to send space shuttles or spacecraft to get these from Mars and Earth. So we are lucky. Meteorites are in general called poor man's space probe actually, because you get it for free. So we have free samples. And also there are some interplanetary dust material that come from comet and asteroids, ablated asteroids. So if you have a low flying aircraft, you can catch this interplanetary dust particles in the stratosphere level. So if you go some beyond 35 kilometers of our Earth's surface, you can catch them and bring it back to lab. So it's an easy way of getting comet samples or asteroid samples. And there are also micrometeoroids. When the ablated meteoroid fall into the system, because of the flash heating, they form like spherules, small spherules, and they become like a micro meteoroids and fall on Earth. So if you collect them from different regions, from deep sea sediments, or from the Antarctica snow, or from the deserts, you get these meteoroids and micrometeoroids. You might find some of them. So in lab, back in lab, I have just put 3 because I didn't want to overwhelm you, but there are n number of instruments that you can use to analyze these materials. You can analyze them for water, organics, element morphology, elements, and see what kind of material was there. So this is something which we are talking on basis of meteoroids. So I just want to, what Debabrata Banerjee, when he was giving a talk, I just put this slide so as to just give you a glimpse. So these whatever I'm showing is first forming solids from the asteroid, from the meteoroid basically. So what you do is take the meteoroid, cut a section, and look at it with a naked eye. So if by a naked eye you will see a amoeba kind of a structure, it's very whitish. This is the first forming solid, which is calcium aluminum inclusion. Yeah. So how do I know it's first forming? You need to date it, right? So you will date this and say if it is first forming solid or not. And this will tell you when the solar system formed, because it's first from the condensation sequence, what mineral will form when. You can calculate it. There's a thermodynamical calculation, and you can say that this can form first or second or third. Yeah. Similarly, there's another object which is called chondrules. They just follow this calcium aluminum inclusions. They form later, within a millennia. They form from dating. We know that they form from 1 to 2 million after CI formation. So what people have done in lab, they have measured the CI's chondrules by uranium lead dating. When you say uranium lead dating, it is a long radioisotopes, and you measure this to get the absolute dating. I mean, it's one absolute dating you get from it. But when you do aluminum magnesium, it's short-lived radionuclide, like what Debabrata was talking about. This is a relative chronometer. Means I will take a CI, I will measure that first one, and then I will do a relative dating of rest of the CIs depending on the first solid forming. Okay, so relative dating. This doesn't give an absolute dating because we are not sure what was the initial composition of aluminum magnesium. I hope it will be more clearer when I go through few more slides. So as an example for this, I'm not sure how much you know about isotopes, but let me still go through this. There is an aluminum magnesium systematics. For aluminum, it's a monoisotope, stable isotope, 27 aluminum. 26 aluminum is radioactive. It will decay into 26 magnesium with a half-life of around 0.73 million years. Okay. 24, 25, 26 magnesium are stable isotopes. And they have a particular ratio of 25 by 24 or 26 by 24 in our solar system, which is pretty homogeneous. Now, if I have 26 aluminum in say CI, which I was talking about, and this 26 aluminum decays in situ, in there, it doesn't communicate with the rest of the material, just within CI it decays. What will happen is there will be an excess of 26 magnesium. This is what we measure. So we measure this excess of 26 magnesium, and then we say that 26 aluminum was present in the CI, and then we date it back. So for dating back, if you are a nuclear physics student, you will know there is a famous radioactive equation, which is N is equal to N0 e raised to minus lambda T. So half-life, I have told you, the initial composition by present composition by initial composition is what you will measure with the half-life. Yeah, and this will give the chronological parameters. So now I have something observable that I see is systematically there. And now I have a chronological parameter of various bodies that are formed that I have in hand. Yeah. So I know this. So putting this 1:1 together, I will try to do much better modeling. Yeah. Okay. So not only this, we have more to add to it. Now, when you're making a model, you need to know the initial composition of the molecular cloud, yeah, from which the solar system will form. So if you look back at the nebula model which I was talking about, it was there was a cloud and there was protostar and there is an orbit of planets that form eventually. But this molecular cloud is not really single molecular cloud. It comes within a giant molecular cloud. So giant molecular cloud is something which has 1 hydrogen per centimeter square. It has few denser molecular cloud within it, which is like 10 raised to 3 hydrogen per centimeter square. And there are cores. The cores are the one which basically gravitationally collapse to form a star or a planetary system. So some cores will form star and some will form planetary system. That's it. It's statistical. Yeah. Now so you know that our molecular cloud from which we have solar system has formed is surrounded by various stars because there were many cores surrounding it. So for example, I don't know how much you know about the stars, but let me still name it. Suppose we had a supernova nearby or a asymptotic general somewhere nearby. These are they are nucleosynthesizing new material in themselves, nucleosynthesizing material within themselves, and there is death of star. When there is a death of star, they throw away the material outside. So any material between two stars, any space that between two stars is called interstellar medium. Yeah. So this interstellar medium is very vacant kind of a system where the material that has been thrown away by a star, a dead star, comes into interstellar medium, and this interstellar medium becomes a part of the molecular cloud. So the composition of our molecular cloud depends on the stars surrounding it. Not only that, there are some circumstellar grains that are formed around the stars that will also fall in our molecular cloud. So not only we can analyze this and tell what was the composition, which stars were basically contributing to our by analyzing elemental and isotopic composition of these grains. Also, there are organics forming in interstellar medium that also comes along with this pre-solar grains. Most of the pre-solar grains, not most, but 50% or 60% of the pre-solar grains are coated with organics when they come into the system. So one of the question always remains whether the life has come from outside, from the interstellar medium through pre-solar grains. So this has been a question, yeah. So now I say that there are stars, there are pre-solar or circumstellar grains coming along with organics, along with other material like short-lived radionuclides or other radionuclides and elements into a molecular cloud, which decides the initial composition of the system. Not only this, you can calculate basically whether the molecular cloud was collapsing self-gravity, within the self-gravity, or was it a triggered collapse? So for a triggered collapse, you need to find out an isotope that is formed in, say, supernova. And suppose supernova is triggering it. So the timeline should be of the isotope should be such that it can talk about the time scales from when the star died to the first formation of solid in the solar system, which has been done in PRL in itself. We have done 41 calcium isotopes to say that probably it's a triggered collapse and the triggering is from the supernova. So there is much of work involved in this, but that's one of the best papers, which is communicated from PRL, which talks about triggered collapse from short-lived radionuclide. Now here I have also shown various pre-solar grains. You can see the size of the grains. They are very, very small. They are micron sized, 1 to 5. When I say 5, it's the largest size probably. They are very small grains, less than a micron. They are in nanometer scales. So when you have to analyze such kind of grains, you need to have a very sophisticated instruments. So that's what Praveen was introducing Vikram, saying that he has one of the sophisticated instruments. So PRL also deals with very sophisticated instruments and works on these kind of grains. So now coming back to formation of solar system, which is topic of my talk. So we will come back to the nebula model. Now this has been evolved with time till now, and I will make some changes, but let me give you a fair view of this system, which is shown here in different parts and parcel. Okay, so first, a cloud of interstellar gas and dust is called solar nebula. Most of it is 98% hydrogen and helium, but it includes atom and dust grains of heavier material from the previous generation of stars. I talked about this, yeah. So now this starts, this becomes thick and either gravitationally collapses or there is a triggered collapse to form the sun at the center. So there is a dense material in the center, and this becomes denser and denser by collecting the material from inside. So a star will form when hydrogen fuses to helium, and this has to form at the center. Okay, but the rest of the material rotating along with the star becomes a flattened disk kind of a structure due to the angular momentum, and this rotates along with the star when the star is still in the forming condition. It's called protostar, yeah, proto sun, you can say proto sun, yeah. Now yeah. So the contraction leads to protosun in the center, and there is an accretion disk, and there is heat which vaporizes the dust. So more or less, this becomes a homogeneous disk or homogeneous nebula in some ways, if you see. Yeah. Now after this, where the grains are very nearby, the grains start sticking to each other. There's no other way you can make a body from dust. So the dust starts sticking to it. It's called coagulation kind of. By sticking, it makes a bigger object depending on how much material is around it. When it becomes a planetesimal kind of a structure, you can say when it can gravitationally attract. So gravitational works only after certain mass. So it will gravitationally attract material from the side by and become a bigger planetesimals. So planetesimals means a stage before formation of planets. Yeah. So this is the time where small asteroids or something are forming. Yeah. And finally, these planetesimals evolve to planets in billions of years. In 100 billion years, probably the evolution of planets have taken. In fact, there are differentiation processes that has also taken place. During this, there's a lot of impact going on. So the planets are being hit by the other objects which haven't been formed, yeah, like from the asteroid belt. So dynamically, it's a very active state, but the star has started basically started the nuclear reactions. So hydrogen and hydrogen is burning to helium, and radiation has started. Yeah, this is the point where we say solar system has formed 100 million years and everything is formed, right? So till 2020s, we are thinking the solar nebula formation scenario is one of the best scenario. This is the best scenario that you can see for the, and it's most widely accepted model. Yeah. But then what happened is that we had a sample return mission. So one of the first sample return mission was the from the Will-2 comet. Yeah. So this was in 2006. The sample was brought down. This is a NASA's mission, and Will-2 comet samples were brought back in something like this is a brick of aerosol. It is a very light material, and you can see tracks in between. These are the small grains that have been embedded in aerosol. So we remove these grains from these, and then we analyze these in sophisticated instruments. Now, what happened was the idea that the comets form in outer regions. I did talk about this, yeah, that all comets form in orbits beyond Pluto. But the material that we saw were not like this. It was the material more like CIs, calcium aluminum inclusion, that forms pretty close to the proto-sun, basically. So from this sample determination, the idea of inner material being mixed with the outer region, which is at 40 AU, it's a long distance, yeah. So there is a long distance. So there has to be a model which states that there are solar winds, which are called X winds, which carry this mineral and throw the material in the outer region, which is far, far away from the sun, yeah. And there is a churning, basically, of the first solids or the inner material with the outer material till the planetesimals or embryo of solar system have formed. Till then, when it is in dust sequence or first forming solids are forming. Okay, so other than this, this changed the model scenario of origin of solar system, and then apart from this came the new results of exoplanets. You had heard about exoplanets. In 2013, I think first exoplanet was reported. Now, if you have heard about exoplanets, you might have heard that they have majorly seen planets of Jupiter size, and they are very close to the sun. That's why they're called hot Jupiters, hot or warm Jupiters. So if you look at one of the system, exoplanetary system like Kepler 11 system, you will see that there are planets. There are many planets. It's a multi-planetary system. But all the planets revolve around the sun within the Mercury orbit. You see that that it's within the Mercury orbit. So what is happening here? Our solar system is unique, or the exoplanetary system that we are looking at unique. So again, there was modeling parameters that were taken care of, and people started thinking again last decade. And since then, they decided there's a new model which was revoked, is of migration of planets. What is migration of planets? There was a theory, Nice model, and there is a second model which is called Grand Tech model. Yes, so Nice model and Grand Tech model are similar. They talk about migration of planets. So what is happening? Let's come back to the embryo stage again. So when the sun is in proto-sun state, first planet to start forming is Jupiter. Okay, Jupiter has a core, and which is like 10 Earth mass or something of that sort. Okay, now Saturn is in a smaller embryo region, and even further small embryo is of Uranus and Neptune. But the Jupiter is being pulled by the sun's gravitation. So Jupiter is pulled, Saturn is pulled, everything is being pulled by the sun. But at a certain moment, when it moves from 3.5 AU, AU is the astronomical unit, from where the Jupiter has formed, it is moved from 3.5 AU to 1.5 AU, where Earth has formed, yeah? Where Earth is right now, around 1 AU. Till there it comes, and then there is a resonance catching between the Jupiter and the Saturn. It's 3:2 Jupiter resonance, it's called. What is 3:2 resonance is when Jupiter takes 3 revolutions around the sun, Saturn will take 2, and they get logged. When they get logged, they have, in this stage, they cannot move further because there is more mass. together moving inside. And till then, the outer region has been swept by this migration. So the total outer material has a torque and inner material has a torque. Outer material torque is lesser than the inner material. So the Jupiter and Saturn start moving backwards, okay, because of this. So the migration is going inside towards the sun till 1.5 AU, then going back to the original position where Jupiter is as of today, which is around 5.2 AU. And then finally, when it's moving, it's also collecting all the material around it. That's why Jupiter is very, very big. Yeah. And it is said that because of the Jupiter's gravitation, there should have been a planet where the asteroid belt is. So the planet couldn't be formed because of the gravitation of Jupiter, and you have small pieces that are thousands of kilometers there and billions of pieces there. So the migration theory is something new that has been added to understand the formation of solar system, that it evolved this way. And these are the few steps, like the mixing of material before this, and then the migration of planets, and to see what we see as of today in the solar system. So with this, I would say I have finished, and all the best for future talks. And I would like to take questions if you don't mind.
Thank you, ma'am. Thanks for the talk. Waiting for the questions. Does resonance explain retrograde spin?
So retrograde spin, no. The resonance doesn't explain the retrograde spin. Actually, I'm not sure about what you're asking. Maybe for Venus, if you're asking, the reason why Uranus and Venus have a different rotation was basically explained by the collision. The dynamics, as I said, was very high. So it is assumed that one of the larger piece of asteroid has hit this in a wrong direction to change its rotational direction. Yeah. So when I say 3:1, 3:2 resonance, let's come to 1:2 resonance first. Yeah. So when I say Aditya, when I say 1:2 resonance, means there is a sun. The planets are orbiting around the sun. So if Jupiter is, there is a time when Jupiter and Saturn will come together at the same place. But because the rotation orbit is different, the rotation might take different time. Yeah. So for one rotation of Jupiter, after two rotations of Saturn, they come close to each other. This is very destructive kind of resonance. If you do a modeling, it is seen that it generates more impact to destroy the material, not destroy actually, to disrupt the material that is around it. So it basically disrupts the inner material, throws the inner material to the outer region of the solar system. And when it comes again, it starts orbiting, and when it is a 3:2, and if it locks, then it is the time when the migration, second part of the migration starts. Jupiter does have a very high magnetic field, actually, Ragan. It is 20,000 times higher than Earth, actually. Why do Jovian, Madhavendra, Mukula, why do Jovian planets have more mass and larger area? Yeah. So the reason given for this is why the outer planets are more heavier than inner planets is again can be explained by migration theory. Actually, earlier it was said, before the migration theory, it was said that it is because the distribution of masses is such that that there are more mass near the Jupiter. That was the initial before migration theory thing. Before I say anything else, I also want to say that you understand that the sun has high temperature. So what is happening is sun is throwing out solar. So there is solar wind and solar energetic particle and heating going on around sun. So what happens is very refractory elements, yeah, which will stay back there. That's why there are solid planets forming near it. The volatiles, more gaseous ones, will go to a region where they can condense. The condensation temperature for the gas material is very low. So they go beyond to a region which is much more cooler. Yeah. So there is a snow line around 3 AU. So they go beyond that and then condense to making a planet. So from migration theory, it is said that when Jupiter embryo started moving in, it basically caught, it was able to catch all the material. So the reason why Mars is smaller is based on migration theory, that it ate away all the material that Mars needed to have. Yeah, and Jupiter grew bigger than anything else. That's why these are bigger planets. How the rings are forming, why they are forming, Gopika, actually what is happening is this advantage means, well, there is no advantage, disadvantage to this probably. But what is happening is, for example, when the core is forming, core has a gravitational pull, yeah. So the core is solid, but the above material, like an atmosphere, is getting attracted to the giant planets. So after a certain time, it cannot gravitationally accumulate all the material that is surrounding it. So that becomes like another small solar system kind of a material. So you can assume that the Saturn is like the embryo of Saturn is like a sun. It's not sun because it's not having a nuclear reaction going on, but assuming that, and a nebula of this ring, that small moons can form. It's dynamics that plays a role here. Okay. How do we differentiate between meteoroids that come from outside our solar system to the one inside? So, Jatin, actually, yeah, any extraterrestrial material should be called meteoroid, yeah, when it lands upon Earth. Now, we had one meteoroid coming from really outside solar system, which has been reported. We never have it in lab, so it cannot be called meteoroid. It can be called asteroid, yeah. So it's not a meteoroid until it falls on Earth. We don't call it a meteoroid. So the meteoroids that we have in lab are mostly from the solar system. We don't have, as of now, we don't have an extra solar system meteoroid, yeah. But there has been an observation of extraterrestrial material, extra solar material coming from the solar system material coming inside. But the eccentricity of this orbit is immense. So by observation, that is how we knew that it is not solar system material. So there is an observation center which observes what is going around the Earth. Yeah. So that's how we know this. Parvati, ma'am, why does the migration of planets take only? Actually, I would say that it doesn't, because the Jupiter is bigger planet. The dynamic play between the Jupiter and the rest of the material is more. Yeah, it's only because of its size that it is the region where it was beyond snow line. The most of the material, volatile material, went and stood there within the snow line region, and the Jupiter was much larger. From the embryo stage itself makes it more important. I would also like to point out here that there is a resonance between the asteroid belt and Jupiter also. So there are various resonance like 5.5:2 or 5:3. And in these lines, you will not see asteroids. There is a gap. It's called Kirkwood gaps in the asteroid belt. If you are interested, you can look at it. So Vic is asking, ma'am, why there is a disintegration after formation of iron and stars core, and if there's a disintegration. So you're talking about stars, supernova, I guess. So what is, I guess from your question, Sovik, please write down if you want to ask me about how the interior of the core is getting disintegrated. It usually happens in supernova. So I need to explain you supernova for this. So supernova, if you look at our sun, it is a very small star. It's just one solar mass, which is 10 raised to 33 kg. It's supposed to be very small star. So this can do only hydrogen. It will ignite 2 hydrogen to make helium. That's all it can do. Yeah. But we have other elements because of the material that we receive from other stellar sources. It's not what sun is producing right now. Okay. So the iron you see in your blood, or calcium you have in your bones or nails, or phosphate you have on your teeth covering that you have, these all are elements which is star bits. Yeah, it's not from the sun, it's star bits. You are made up of star bits essentially. So this is coming from other stars. Now other stars, they are producing, like supernova is producing it. For that you need to have a star of mass greater than 8 solar mass. So if you have a star mass more than 8 solar mass, the helium will go into 3 helium reaction, which will produce carbon. Carbon will go to nitrogen. Nitrogen will go to oxygen, and all series of the periodic table from there till iron will form. At iron, it stops. Why? Why the fusion stops? Because iron has the highest binding energy. Okay, at that time it stops, and further addition of any material will not form higher material. But what happens is there is a disintegration, because there is the core starts because there is no reaction going on. The core of the starts contracting. It contracts and degeneracy is formed within the system, and there is a implosion basically. So that's how all material is being thrown away. That's how a supernova dies and throws away all the elements it has synthesized during all this time, whatever is there, and this material is then thrown into the interstellar medium from which the molecular cloud is born. Am I clear, Souvik?
I think there are no more questions. Thank you, ma'am. Thanks for the talk.
Thank you, Vikram, and thank you, Praveen.
Yeah, thank you, Professor Kuljeet, for a wonderful presentation and taking us to billions of years back, which we can't imagine at all. And also, I would like to thank Mr. Vikram for nicely moderating this session. Thank you all the participants, and we will meet again tomorrow in the same time, 3:30. Thank you. Bye-bye.
Thank you.